Properties of isosceles triangles. First of all, we have to understand the vocabulary for an isosceles triangle. And this is handwritten, so I'll read to it. Angle C here is our vertex angle. The vertex angle is always the angle that's between, it's the angle that's between the congruent sides. And so this side and this side are equal. And so the vertex angle is the angle that's between them. The angles at the bottom then, I shouldn't say at the bottom, I don't want to say it that way. The other two angles are called base angles. And then the side that connects the congruent sides together, or I should say the non-congruent side, is called the base. Oh, I'm sorry, I skipped over the fact that the congruent sides are the legs. So the congruent sides are called the legs. The non-congruent sides are called, their side is called the base. And the angle opposite the base is called the vertex angle. Okay. This red ear-shaped thing is separating that other triangle. I want to talk about that in a minute, but I'll let you copy this picture down and then we'll talk about it. The problem is a lot of people think the base is the side it's sitting on because your basement is the structure your house sits on. The base of a vase is what the vase sits on. All these things are what we consider the base. But in an isosceles triangle, you have to remember the base is always opposite the vertex angle, and it's always the side that's not congruent to one of the other sides. So when we go over here, if I label this so we can talk about it better, which segment is going to be our base? Segment AC. It's not sitting on segment AC, is it? But it's still the base because it's opposite the vertex angle and it's not one of the congruent sides. So that makes angles A and C what kind of angles? Base angles. Okay? So don't get trapped into that logic, well, the base is always the side it's sitting on. That's not true. Okay? Just put it down. Okay? So again, here we have an isosceles triangle. What's different about this is which angle is the vertex? Vertex angle, I mean. B. B is not acute this time. It's an obtuse angle. That's the only reason I drew that picture there. Just so you can see it's not always an acute triangle. Sometimes it's an obtuse triangle. Okay? All right. Moving on. Isosceles triangle theorem. In some books they call it the isosceles triangle base angles theorem. Excuse me. It's a little long-winded, but it gets to the point of why this theorem exists and what it says. It says if two sides of a triangle are congruent, then the angles opposite those sides are congruent. All right, so looking at this picture, excuse me, which sides are congruent? Segment AB is congruent to segment CB. Okay? I agree with that. Now, since those two sides are congruent, then this theorem says what angles will be congruent? Angle A, which is opposite segment BC, is going to be congruent to angle C, which is opposite segment AB. And so, in other words, the base angles will be congruent. And other books wouldn't label, or wouldn't name, let me try again. They wouldn't describe it quite like this. They might just say base angles in an isosceles triangle are congruent. Okay? I understand why this book uses this approach, and it makes a lot of sense. When we get to the corollaries that go along with this, it'll make a lot of sense why they use the terms the angles opposite instead of just saying the base angles. But you can remember it however you want. If you just want to say, hey, base angles in an isosceles triangle are congruent, that's great. But it's because of the isosceles triangle theorem. Okay? Isosceles triangle theorem. Probably, you know how lax I am about caring whether you put theorem or postulate or something like that on there? And because of that, I usually say I don't even care if you put it on there. But in this case, if you just say isosceles triangle, it's like telling the first half of the joke but never giving away the punchline. Without saying theorem or mistakenly calling it a postulate or a property or something like that, we don't understand what you mean by that. If you just put your reason as isosceles triangle, then, well, that's great. It's an isosceles triangle. What's that mean? Right? It's this theorem that tells us, well, if it's an isosceles triangle, then these base angles have to be congruent. Okay? So you have to put something other than isosceles triangle in a proof if you're to use this.
Can we put ITT?
Yeah, I could get used to that. I've never ever had anybody ask that, but I could get used to that. ITT. Okay. The converse of the isosceles triangle theorem I'll move this right back up. I'm just going to label it so you can see what a picture looks like. Converse of the isosceles triangle theorem. Food. Yeah. All right, while some of you are finishing this up, let's just talk about it real quick. It says if two angles of a triangle are congruent, then the sides opposite those angles are congruent. So these two angles are congruent, angle A and angle C. So what sides will be congruent?
A, B, and C.
Yeah, the side opposite angle A is segment BC. The side opposite angle C is segment AB. And so they're going to be congruent. So this is what kind of a triangle then? Isosceles triangle. Okay? So it's important that you understand in a triangle. In a triangle, this doesn't work for other polygons, but in a triangle, if you have two congruent sides, then you have to have two congruent angles. If you have two congruent angles, you have to have two congruent sides. If you have none of your sides congruent, then your triangle can't have any congruent angles. If you have none of your angles congruent, then it can't have any congruent sides. Okay? There's another rule we need to understand. This is the bisector of the vertex angle of an isosceles triangle. I'm not sure why I put that comma between isosceles and triangle. Is also the perpendicular bisector of the base. Triangle, my comma should really go over here. There. The bisector of the vertex angle of an isosceles triangle is also the perpendicular bisector of the base. Let you copy that picture and that down and we'll talk about it. Alright, so what this is saying, since I know this is an isosceles triangle, first of all you have to know it's an isosceles triangle. Then you have to know that this angle and this angle are equal. That means this is bisecting that angle. So if that's the vertex angle and you bisect the vertex angle of the segment, then this segment is also perpendicular to the base, making these what kinds of angles? Right angles. And it's bisecting the base, cutting it into two equal pieces. So that means AD is congruent to CD. Segment AD is congruent to segment CD. So you can see how that would be helpful to us, wouldn't it? We're writing proofs. We want to know this segment is congruent to this segment. Okay, we want to know these angles are congruent. congruent and supplementary, so they must be right angles, right? They are right angles, so they have to be congruent, all right? So, a very informative rule they give us here. It will help us. Now, all these things together give us the ability to do a lot of different things with proofs. Yeah? Nothing. Okay. A corollary. A corollary is a true statement that follows a theorem to give us more information.
Winder.
No.
The one dimension.
All right. A corollary is a true statement that follows a theorem to give us more information. Okay? So another vocabulary term. When you see that something is a corollary, you just know that it's additional information that's added on to a theorem. And so the first corollary we're talking about today says if a triangle is equilateral, then it's equiangular. Well, this is attaching to the, if two sides of a triangle are congruent, then the angles opposite have to be congruent. This one's saying if we expand that to all three sides are equal, then that means all three angles opposite them have to be equal. So if a triangle is equilateral, then it's equiangular. And the second one is just the converse of that, going with the converse of the other one. Saying if a triangle is equiangular, then it's equilateral. So, what we're saying in corollary 1, if I know these three sides are equal, then that means all three angles have to be equal. The angles opposite the congruent sides have to be congruent. So if all three sides are congruent, then all three angles have to be congruent. And likewise over here, the sides opposite the congruent angles have to be congruent. So this is just a corollary that goes along with that. So if you had to use this in a proof, you know, there's no name to it. You wouldn't say corollary 1, corollary 2, because that's just how it's numbered right here. It doesn't mean anything. You'd have to say triangle is equilateral, then it's equiangular, or you'd have to say if a triangle is equiangular, then it's equilateral. Okay? Or you might say it this way. Equilateral triangles are equiangular. Or equiangular triangles are equilateral. You can just say it as a matter of factly like that. You don't have to make it a conditional if-then. Okay? Any questions on that? All right. Your assignment today, lesson 4, 5, 1 through 652,
Multiples of 7,000.
all. Oh, just kidding. 1 through 25, odd. Odd. Okay?